All right, hi, I am Nathan Danneman. I'm going to talk a little bit about this thing that I'm calling rule breaker. Really, it's just exploring categorical correlations as probabilistic rules. That'll make a lot more sense to you in a minute. If that makes you yawn, just kind of hold tight for 30 seconds. Okay, a bunch of huge thanks. The BSides people, staff, especially Daniel, who helped me figure out what on earth I was going to be doing here. You guys are awesome. You lined up great speakers. Big thanks to the earlier ones. I'm going to stand on the shoulders of those giants a ton, especially Tim, who said, who made a 9 great points about why machine learning for InfoSec is really, really hard. I'll be jumping off from that a lot. I'll also talk a lot about, jump off from the first talk about rules and inducing rules from indicators of compromise and kind of marry those things a bit. I didn't realize that this thing was going to be ordered this way, but if this was the intention, great job. Big thanks to a company called Data Machines. I work for them. They're kind of a small outfit. They do kind of statistical consulting. They also stand up fancy private clouds for customers who need that kind of stuff. We're not a product company, so I'll be talking about this thing that I've given like a name to, but you can't buy it from me, but I can give it away to you for free, in part because Uncle Sam helped fund part of it. Big thanks to the government doing lots of kind of high-end R&D in the cybersecurity space. It's mandatory that I have that gray stuff on the slide. There it is. Okay, so we're going to talk a little bit about big data and analytics for cyber defenders, and that's going to really riff on some of the things you've heard this morning already. I'll talk about this thing, rule breaker, which I like to say with like, I don't know, some kind of bad Scandinavian accent, right? Like, rule breaker. We'll talk about how it works and what it is. I'll talk about how to try and make it security relevant in its use cases. And I'll talk about next steps a little bit because this is active research. This isn't kind of a beautiful shrink wrap thing that I'm kind of extraordinarily proud of. And again, it's not a product. You can't buy it from me. Data Machines doesn't sell anything except people's research time. So it's nice I get to kind of make fun of people who sell things, which was me as of a couple of years ago. Really brief background. I'm kind of an applied statistician. So perhaps much like Tim, who I think is no longer here and can't defend himself, which is perfect. I know enough, I guess, about mathy stuff and have picked up a lot of networking stuff on the fly over the last 4 or 5 years. But networking, computer, cybersecurity, it's a really, really big space. So I broadly claim a lot of ignorance there. So if I say something silly, just give me the benefit of the doubt, or come tell me later. We can dream up new use cases. At the end of this, what I'd like to do, what I will do kind of in brief, is show you how to code this thing for yourself. It's easy. Even if you're not like much of a coder, it's still pretty easy. So that's kind of the kind of goodie bag at the end of this. Hopefully that'll keep you engaged for like no more than 30 minutes. Okay, I'm going to set up this kind of topology of ways we could do cyber defense that are data-driven, and then I'm going to break it. Just kind of for kicks, because breaking things is fun. So one way you can do defensive cyber analysis is with rules. So the idea here is let's encode knowledge in a bunch of kind of if-then statements. These are often like known bad actor TTPs, which I'm told stands for techniques, something, and practices. But you can also get these from IOC lists, as the first presenter talked about at 8 o'clock this morning, if you caught that. So an example kind of tooling here is something like snort, and you get rules, hard and fast ones, that look like if some IP and some port or some other domain, then block it, report it, alert on it, stick it in a queue and never look at it, whatever you're going to do. So these have some real pros, right? These things are understandable when some jerk face like me hands some real cybersecurity expert a possible issue, and they say, well, what makes it an issue? You can just say, look, if bad guy domain, then bad guy stuff. If there's a bad guy domain, it's really easy to understand. They're targeted, they're fast, both to implement, though maybe if Dave was here, he'd be telling me I'm kind of making too small a thing of that. They're also super fast to execute, right? You can do these often at line speed. Big cons, though, these things are pretty simplistic, so they sometimes leave some things to be desired. Bad guys can kind of sidestep these things pretty easily by changing small characteristics. Another big con here is the kind of known knowns thing. So if you have a bunch of rules, you can catch known knowns pretty reasonably, but you're kind of helpless still with respect to kind of things you don't know about. And that's either because the IOC lists come in kind of slowly, or they're bad actors. They're just slightly more clever and they're kind of changing things on you. We could talk about catching 0 days. That'd probably be a lie, but we'll talk more about that in a minute. Okay, defensive analytics 2. So you want to like not necessarily level up, but take like a different approach. Maybe we do statistical pattern matching, which was the whole thrust of Tim's talk, right? The idea here is you get a bunch of examples of, for instance, malware carrying PDFs and a bunch of benign PDFs. You learn some statistical model that differentiates those two. You put that model into production, and it says, that's a good one, that's a bad one. That looks like the good ones I've seen, that's a bad one. Just one of many examples of people who do things like this. FireEye, Cylance, there's a slew of these guys on the market right now. Statistical pattern matching, aka supervised learning, is sweet in that it is targeted. So you're going to like have these really specific models to try and separate bad guy stuff, MS Word attachments from benign ones. And they can be quite accurate. In spite of all the very real problems Tim alluded to, you can get pretty high accuracy out of these things. Of course, you know, if you're getting it right 95% of the time, you're getting it wrong a lot, right? Because people are slinging a lot of files. Cons, though, as Tim really nicely alluded to, you need training data that's labeled. So you need examples of, I don't know, regular people MS Word files and a bunch of bad guy containing MS Word files. You also get, like he also very aptly pointed to, you get these crazy uninterpreted models. So I send results to the cyber SME that I sit next to, and he or she goes, what is this? Why is this bad? Why are you sending it to me? And I say, oh, we're gonna have a long, awkward conversation where I basically acknowledge that I don't know how to interpret my own models. These things also have a really short shelf life. I think, man, that Tim guy really crushed it. As the data changes, as the threat space changes even slightly, your models get stale really quickly, just like your rules also subject to the same problem. And you need many models to achieve broad coverage, right? You need like, and this is totally painting a childish version picture of this, but you need like the Microsoft Word 2003 separating model and the one for Word 07 and. So you need tons of these models, and you have to kind of keep all of them up to date and deal with all the issues of them becoming stale and interpretability, like times every model you have in your whole system. Yikes. Okay, so there's like another way you can kind of use data to try and defend networks. I guess I should have mentioned, I worked at a company, maybe or maybe not that company, for a long time doing this and other things. And recently I've been kind of doing cyber R&D for the government for a bit. So that's kind of where I have the kind of visibility to say some of this stuff, maybe authoritatively, maybe not. The idea here is let's use a statistical model to describe normal data, right? And if I can describe normalcy, kind of ipso facto, anything that doesn't fit tidily in that bucket is anomalous. I know IronNet does it because I wrote models like this for them. Or you can also try and model the anomalousness of observations directly. Huge field on that. If you care, I'll point you to other papers or talks. Pros here is you get these really cool dynamic models that like can update really easily over time. You get per environment customization, right? So I don't try and apply some generic model to like all these different enterprises that have really different stuff going on. And you can detect unknowns, which is super sexy. Like when you say that in a sales pitch or to the government, they're like, oh, unknown unknowns. That's like, I don't know, the sine qua non thing. Problems, big problems. These things are super noisy, and that kind of fact derives from the really simple notion that weird feedback over there. Everything that's anomalous is not necessarily malicious. The internet, because of super casual design and usage patterns, and because we need our admins to have broad freedoms, do weird, highly anomalous stuff that's totally benign all the time. If 1 in 1,000 things is anomalous, and you have big data, so there are a bajillion things going across your network, all of a sudden you have, you do some simple math and you realize that there's going to be a ton of aberrations, definitionally. Your definition of what is an anomaly like implies an algorithm for detecting that type or class of anomaly, which implies what your result set will be. And TLDR, anomaly detection is really, really complicated. It's easy to mess this up in ways you won't know about. And you also get these terrible uninterpretable models. Okay, so that's the paradigm I've set up just to kind of knock it down. I'm going to talk about this rule breaker thing that gets you hopefully some bits and pieces of the power of all three of these approaches, and to some extent, and we can discuss this afterwards, Again, it's nice that this is not a sales pitch. It sidesteps a lot of their pitfalls. So the high-level idea behind this thing I'm going to eventually get to the point and describe to you is that we're going to generate simplified models of normalcy in the form of probabilistic rules, right? So I'm going to look at your data, and in your data, if port 53, then DNS, likelihood 99% of the time. We're going to infer that from your data, and then we'll go back through your data and try and identify observations that break that rule. And we'll talk a lot in a minute about how to identify security-relevant rules as opposed to just correlations nobody cares about. You get dynamism, you get some unknown unknowns here from the anomaly detection part of this. You get the interpretability of a rule, so I can pass these results to the cyber SMEs really gracefully. And they say, why is this weird? And I say, look, because in the data, like if A and B and C, then D, but here if A and B and C, then F, and they can use their mental model of networking to decide if that's bad or not. And then you get some of the accuracy from statistical pattern matching. These rules are probabilistic instead of deterministic, which means they hold most of the time. And then again, the cyber SME can determine whether they're like, I give a crap about a breakage of this rule, or that rule is really silly. Okay, a little bit more motivation. So network data, because of RFCs, convergent use, habits, you often get these strong interdependencies between fields or variables in your data. So think, if you're looking at NetFlow data from YAF or Bro, or you're looking at, host level data from insert name of your favorite agent here, you get these strong correlations, right? File extensions that imply or go with MIME types, ports and protocols. The second bullet is kind of neat because here we can start to talk about ranges of continuous variables like return bytes, right? So like if I'm doing port 53 and it's a quad A record, and you get back a bajillion bytes, that's kind of atypical. Port numbers correlate with protocols. And so the high-level idea here is, what if we can automagically identify strong categorical correlations, right? If port 53, then probably DNS, to learn about a network. And this is great if you're on a consulting team or like some of the folks I've worked with in the past on the government side that go to different networks every month. If you work in the same SOC for the same corporate entity for like the last 5 years, you probably know your network inside and out already. Maybe that's not cool to you, but then you still get the second thing. So we can then, with these probabilistic rules identified, again, really simply, even if you're not a coder, you can then identify breakages of them to learn about anomalies, and then we'll talk a little bit about how to pick the rules and the breakages that are actually security relevant, right? To get you over the give a shit threshold. Okay. Hey man, can't we just find like people who are using DNS but not on port 53 with a SQL query? Like, that's the first thing my analyst said to me. And it's a super good critique, right? Like, hang on, fancy math. Like, I've got SQL, I've got a database, get out of town. Short answer is yes, if. So if you already know what mismatches you might care about, right? So if you already know you want to look for things not identified as DNS by your protocol inspector over port 53, then you just query that, right? Select star where, port equals 53 and protocol not equals DNS. But if you don't know what to look for, again, the unknown unknowns, SQL doesn't help you there. And then, if there's only a few mismatches you care about. So if that list of mismatches you care about is like of order, tens of them, sure, query them up if you think that's a good use of your time. Maybe script that querying to automate those things. That's nice. But what if there are an arbitrary number of unknown mismatches that you might care about? You can't SQL that. Okay, and isn't this just anomaly detection? Like I kind of laid out point 1, 2, and 3 for defense with cyber data, and I said this is kind of like overarching blah, blah, blah. But this is really just the third one. Sort of, it certainly starts out that way, right? We're certainly going to model normalcy, but we're going to do it in a really particular way. This thing is optimized for categorical data, which that just means instead of a numerical thing like height in inches, it's a categorical thing like color in the RGB kind of. Oh, that was a terrible example. Like color in the Crayola 8-pack. This thing is really performant in the face of irrelevant variables. So you can put in lots of fields, and if there are fields or variables that don't correlate with anything else, this thing doesn't care. Lots of anomaly detectors don't have that characteristic. And this one, importantly, is focused on near misses, which makes it really potent for security purposes. So a lot of times, because of adversarial intention, your adversaries aren't fielding inputs that are tremendously anomalous. They look just right in a lot of ways, but are off in like one feature or something. And this thing is optimized to detect that. Okay, let's talk a little bit about the language of rules, because what we're going to do is we're going to induce them from data. So rule breaker thinks of categorical correlations, right? Again, I'm going to go back to this kind of trivial example, and we'll talk about all the complications that arise in a bit. But if port 53, then protocol is DNS, right? That's a strong categorical correlation, right? An example, oh, there's my toy example, and it kicks out a probability statement for that. This is just a simple conditional probability. Note that these are descriptive rather than normative. So this is not a thou shalt rule. This is, I saw in your data this correlation holds rule. So breakages of it are just breakages of correlations. And rules, I'll talk about this using these words. They have three parts. They have a predicate, so if predicate. They have a consequent, then consequent, and then they have a conditional likelihood. So like, that last little thing. Again, if you're thinking, oh God, how do you code that? You're going to get all that for nothing if you use Python, R, or Spark. So we'll talk about other things you can layer on top of that you might want to code yourself in a minute. Okay, so at a high level, here's the kind of game plan. Association rule mining is kind of this big area of data analytics that goes back like 30 years. And it's the task of identifying antecedent sets highly likely to imply a consequent, right? So find these correlations. That's the name of the high level thing if you wanted to Google it. Like, what's association rule mining? And all the packages in those programming languages I talk about reference it as such. Right? So it originated with market basket analysis. So you're running a supermarket and you want to find strongly correlated items from sets of things people buy, so you can co-locate those items in the store. Because it's really annoying when the pickles are with the sandwich stuff and the olives are elsewhere, but in your mind you organize that store according to things that go in cocktails, right? And those things should be together. So for example, bread and peanut butter usually implies jelly. There's a citation if you want to go look at an early one. So the task involves identifying frequent item sets, so things commonly bought together and for our use cases, right? Cyber things that tend to correlate. And then you use those to identify rules. Two-step process. Again, you're going to get both of these for free, so I'm going to be brief about this. Okay, frequent item set. A frequent item set is just a set that occurs frequently. I love it when things have good names. You specify some level of support S, which is the frequency in some big data set that a set must meet before you are going to call it frequent, right? These folks, Han et al., back in 2000, came up with this excruciatingly clever way to find these things that's parallelizable and wicked fast. If you're into algorithm development and you want to see just a pristine example of data structures as algorithms, go look up this paper. I read it 4 times. I'm still not sure I understand the ins and outs of it. It's just lovely. But basically, you scan a database once to find a sorted list of frequent items, singletons, and then you grow a tree based on relative conditional frequency, and you use that tree structure to rapidly kind of pull these things out. Again, if you're into that, great. If you're not, you don't have to know this or code it yourself. You're going to get it for free in some package. Okay, so suppose you have all these frequent item sets, right? Peanut butter, jelly, bread, they go together all the time. A rule is a unary split of one of those things where the likelihood of the consequent given the predicate has some minimum confidence. Oh God, these words. So an item set might be A, B, and C. A unary split is any split that leaves one of those things on the end. And so the rule might be something like if A and C, then B with probability 96%. Right, so that's what the algorithm is doing under the hood. Find frequent items, check all the unary splits of all the frequent enough items, and see if they land with a high enough probability that you care. All right, so rule induction is that thing. Okay, no one is here to learn about association rule mining. We're all here to try and learn about cybersecurity stuff. We get 2 things from association rule mining, right? We learn about patterns in the network. So this client uses DNS, and because they think they're clever, they point it over some odd port, right? Particular services might be strongly associated with particular usernames, et cetera, and we can get all that kind of stuff for free, which is great if you're going into a new network kind of blind, which has been my experience more times than I care to say. And then again, we want to do this kind of anomaly detection task to find all the bad guys, right? We're going to identify discrepancies. So maybe there's this if port 53, then protocol is DNS some high percentage of the time, right? That's the rule. That second thing is a breakage. So you're going to sweep back through the data, identifying sets that have the predicate and not the consequent, right? So I know how IPs work. I shorten all the IPs just to make sure I don't accidentally, in my toy examples, point to a real IP. So like 123 sent ICMP traffic to 456 over port 53. That'd be a breakage of that rule because the rule is if 53 then DNS. But here we have 53 in the ICMP. So we're going to find things like that, and you get those, all the rules and all the breakages, you kind of get them for free, and that's nice. Okay. But these are just correlations. Correlations, especially in really big data, are everywhere. Most of them are meaningless. How do we generate ones of these that are security relevant? If you're thinking that, you're asking exactly the right question. So a couple ways: choose the right features, make sure the rules are statistically sound, and then automate the dropping, right, the trashing of uninteresting rules and breakages. Okay, so some security relevant rules and breakages. One thing you want to do here is choose security relevant features or sets of features where breakages of correlations therein are going to be of interest to you as an analyst, right? This is you using your noggin. Math doesn't get you this. This is where your kind of creativity and expertise needs to come in. So for example, an example that I run everywhere because it's nice and intuitable is to check for strong correlations in the inferred file type. So if you're using NetFlow a parser like Bro or something, it'll say, hey man, here's this file. I think it was a text file, and the file extension was .txt. We think those things should match up. We know that they're security relevant because bad guys like to, stuff, I don't know, an executable into a PDF. Again, if you knew that one use case, you could just find that with SQL, a SQL hook to whatever your database is. But if you didn't know all the ones that might be security relevant, you can use this tool to kind of have them served up to you for free. Okay. Some other kind of examples I'll use. Please don't furiously jot these down. We'll make sure these slides are public. Okay, the other thing you can do is check for metrics. So all of these packages give you this thing called confidence for free, which is that stupid thing, the support of A and B, right? So the count of the number of times peanut butter and jelly are bought together, divided by the support, the count of A. You can, this is directly convertible to a conditional probability, probability of B given A. This is nice. This one's better. The only difference here is we've added this little multiplier by the support of B, so we penalize really, really common Bs. What does that mean? Here's a garbage Venn diagram from 5 years ago when data science was new. Suppose we find this rule, right? If machine learning, then data science, right? The confidence is going to be really high because all of machine learning, hypothetically according to this author, is data science. Confidence equals 100. But what you'd find with the lift is that everything on here is data science. So some rule that is if something, then data science is not all that interesting. So lift kind of goes in and penalizes those really common Bs. So lift is a better metric. Again, you get lift for free in R, Python, and Spark. You have to write your own. It's not hard. Okay, and then the last thing you're going to want to do, even if you've taken these steps to pick good features and use the right metric for figuring out which rules are cool and which ones you're not going to care about, you're still going to get garbage rules. And I don't mean incorrect ones, I just mean boring ones. If the MIME type is text or HTML, then the extension is HTML with a high probability. You find some breakage. Someone's got a MIME type of text/HTML and extension .txt. It's the bad guys. It's not the bad guys, right? You don't care. So the team I'm working with now, we implemented an exceptions list, which is a way to kind of whitelist rules, parts of rules or breakages that we know we don't care about. So we run the same use case a second time, either on the same network or a different network or the next day or whatever. We don't have the results we don't care about served up to us, right? So we could say hey, anytime the rule has .html and the breakage has .txt, don't show me that. So it's a real simple way of pruning these things. We wrote this awful little kind of mini language to get parsed into that thing. I'm way more of a statistician than a coder. I don't know. Sorry, I'm not sorry. Okay, here's a quick example. So again, because a lot of this was done on the auspices of the government and on people's data that they won't let me talk about in detail, I'm going to be just a tiny bit vague here. So sorry, the part where I then show you all the thousands of bad guys I caught with this thing. I can't point a lot of fingers, but just take this as a nice exemplar. We think MIME type should be tightly coupled with file extension, or vice versa. The rules they have an arrow, but there's no sense of causality or directionality under them. All right, and we know breakages of this might be interesting because of anecdotal evidence, right? That thing I just mentioned, right? It says PDF, but look, what's under there? It's an executable. Uh-oh. So we have anecdotal evidence that this kind of breakage might be interesting. And then we've got the unknown unknowns problem, right? I don't just want to find where someone stuffs an executable into a PDF. I want to find all the examples where someone has stuffed potentially weaponizable things. I'm not even sure I know. I can't enumerate that list. I certainly can't. Some of you could probably start to. And stuff weaponizable things into file extensions that are more typically benign looking. All right, so let's go find all of those things in my example data set, which hopefully I've anonymized appropriately. If you're looking at Bro, one of the breakouts, and that's just a kind of a very standard NetFlow parser, you get this breakout that strips out file names, so you can pull the file extension off that really easily, and the inferred MIME types. So what does Bro think this file is coming up the wire? Here's some of these example rules that I found in this one data set, and you read this as, antecedent implies consequent with confidence. I'll just point you to the second to last one. If the application is an executable, then the file extension is DLL 0.999% of the time. Well, what are these things without that file extension? Well, let's go find those automatically. I'll also just point you to those top two rows and note that rules are often kind of bidirectional, but not necessarily the same confidence. So rows 2 and 3. Most of the .xmls are application/XML, and all of the application/XML are .xml. You often get those kind of relationships because these are strong categorical correlations, but having different confidences in both directions, totally typical. Let's see previous Venn diagram. Question? You said turn it up? Yeah. That makes more sense. All right. Okay, so here's some example rules from some example network. We dug into one of these findings that Roy just pointed out to. One of the breakages was this thing, right? So some IP pulling down that file type with a .txt file extension. Note that this is kind of a starting point for an analysis where some of you cybersecurity professionals can then dig in, pivot from the IP or the file or the hash or whatever, and go do the magical things you do. This is basically a high quality tipper, I think, I hope. This is usually the starting point for an analysis, not kind of the end point in most cases. So, but hopefully, again, we've gotten something pretty digestible, right? We did fancy pants anomaly detection. We generated a rule. We found a breakage of the rule. I can send this to a cybersecurity professional who can interpret it immediately using their kind of wet neural network and figure out what to do next. Okay, you want one of these for the fourth time maybe. I don't sell stuff. I give stuff away, and I make stuff. I solve hard problems for pay. So we can talk about those things if you care to. If you want to infer rules, in Spark, there's this thing called MLlib, and there's a frequent pattern mining module, so you get frequent item sets and rules for free. In R, there's this A-rules package. In Python, there's the frequent patterns import, a module for that. The rule checker, so what do you have? For free, you get rules, which is a set and a consequent, and usually a confidence level. If you want to check those rules, you got to write that yourself, but it's super easy because you just say, if my original set has the predicate and not the consequent, rut-row, and kick that thing out to some file. If you look for rules that involve lots of variables, so I've had all these toy examples with a single predicate and a single consequent, right? If port, then protocol. But you can have very complicated rules like if A and B and C and D, then E. A lot of times what I found in practice is those things tend to be nested, right? So if A and B and C, then D. If A and B, then D. If A, then D. If B, then D. And usually the most interesting one to look at is the most complicated rule that was broken. So if you go roll this at home this afternoon in a couple of hours, add that feature, you'll be glad you did. Also really simple. Confidence is baked in R and Python and Spark. R and Python have lift, and Spark you have to write that yourself. The formula is quite simple. The exception list, you're going to want one. Again, that's very easy. You just identify with whoever you're working with, your SMEs, or you are the SMEs. The rules and the breakages that are boring, and write a little way to not be shown those the second time. Okay, here's a part where I am at pains to tell you a couple of the good things this thing does, and then remind you of all of its limitations, right? Lest you think I'm another person saying I've solved cybersecurity with math. The strengths here are its broad applicability, right? So we have lots of categorical features in cyber data. Continuous things can be made categorical by binning. It's only really limited by your imagination of intelligent and kind of informed use cases. You get great explainability here. I've worked with SMEs both on the commercial side and on the kind of corporate side and for government, these SOCs. When you hand them garbage or uninterpretable findings, they hate you. This doesn't have that problem. It's really fast, both to implement and to execute. So it's quick in Python and R. It scales in Spark, which is really nice if you want to hit like the last 6 months of NetFlow data from your big, I don't know, your enterprise holdings or something. And then tuning this is trivial. Tim didn't talk about how machine learning often has these hyperparameters. So they're like choices you have to make about which algorithm and how to set up the algorithm to find the things you're looking for. Tuning can be really hard, and this thing doesn't really have tuning parameters except the confidence level that causes you to care. If you've done machine learning before, you'd know that not having a million knobs to turn to get this thing dialed in right is nice. Okay, and then pitfalls. We talked kind of ad nauseum about how high confidence rules are not necessarily interesting. Pick the right features, use lift instead of confidence. You have to use categorical data for this thing. So you can do binning. If you've ever thought hard about how to bin continuous things into categorical things in a way that's not lossy, you'll know that that's non-trivial and there are lots of ways to do it. You can't do it without losing something. This tool only identifies what I'll call orthogonal outliers. So I think of that as a strength, right? So we're looking for these anomalies that are only different in one way. They're not like broadly different than a set. If you have that kind of problem, like show me the things that are really, really weird, this isn't the tool for that. And as of yet, this whole setup, it doesn't handle a multi-item consequent. So all the rules are these unary splits. If A and B and C, then D, not then D or E. And so if you have a categorical correlation that has multiple parts at the end of it, you can't find them this way. That's kind of future research for me and the team and where I'd like to go next. All right, and that's it. Questions? Yeah.
So on your last point, if it came up with something, could you just not like cascade it, put it in a loop and just running it over the same stuff? Like,
Not sure I follow.
There was one console, it was one with consequence required, so it's like
Yeah.
bread and peanut butter, I got jelly, but it's no good at finding, it's also mustard and tomatoes and all this other stuff.
Yeah.
If you want to find those in the same data set, I run it through with some jelly.
Yeah. So I think I'm tracking your question now. Could you?
Take all the stuff I rejected, run it through again, and get mustard on the second pass.
Yeah. So that's a great thought. Could you kind of? The question was, could you identify those kind of multi-item consequence by using some kind of recursion here? The answer is, I think so, maybe. The problem is in the original set, so imagine you would have found a rule that's like, if tall, then basketball player, or if tall, then pole vaulter, right? And each of those happen 50% of the time. You can't find that rule unless you lower the confidence level you're looking for down to 50%, at which point you're going to find a lot of illusory correlations.
But I can't run it and have it say pole vaulter or basketball player? You mean like that's the output of the two things?
Could that algorithm be written? Absolutely, I plan on it. Let's talk. Can you get it canned like this afternoon? Not to my knowledge. Yeah. Okay.
How do you handle like new service that you stand up with legitimate traffic? How do you ensure that doesn't get market?
Yeah, the question was, what if you stand up a news service with legitimate traffic? How do you make sure you don't fall afoul of this thing? So there's several ways to kind of go about that, right? One is, don't generate rules the first day of the service, right? Like, and that's a whole, we've now kind of like abstracted away from, okay, that's a nifty method. How do I use this thing in practice, right? Operationally, lots of options there. One, like induce rules like, I don't know, one day and then use those rules for the next couple of days, or use it post hoc, right? So for yesterday, I found these strong correlations and these breakages. That kind of helps you get away with the news service problem. If you want to hold rules and like use them like into the future, you're going to have to be savvy to the fact that you've changed your environment, right? And again, I'm going to kind of default back to that exceptions list, right? You hand a bunch of things over to your SME and you say, hey, I found these breakages of these rules. They say, oh, I don't care about anything that involves new service X from before the 10th because that was new that day.
So if you decided, oh yeah, this sounds really cool. I mean, where do we go next? GitHub or something, or how? What's the next thing?
Yeah, I want it now. That's awesome. I'm glad it was mildly convincing. So you can infer rules here. So that's for free. No coding kind of acumen needed by you. You're gonna have to write your own hooks to get data from wherever it lives. Your sim tool into Python, R, or Spark, or something. The rule checker is, again, you write it yourself. So it's just if this set I'm looking at contains the predicate and doesn't contain the consequent, that's a one-liner. That's an additional one-liner that is useful. 3. 4 is you get lift for free a lot of the time, but if you want your own lift in Spark, you have to write it. I don't know if I'm going to be allowed to kind of share the code out from this project yet. If yes, then I'll try and blast out this community. If no, you'll write it yourself, and that one's the only one that's not kind of a one-liner. And then this thing is something you'll, for now, make for yourself. Yeah.
I thought that what you might be saying, but I also thought, well, maybe rule breakers is the thing I go get. This is the secret sauce, this is the design pattern.
Yeah, and it's not secret except insofar as I haven't been given the thumbs up to kind of like push it out there. Yeah. Other questions? There's like a hint of barbecue wafting in, and I think everyone's ready to get out of here. All right, well, that's all I have. I'll be around through the end of the day, so if you have questions kind of later, come find me. Otherwise, I'm not going to be between you and your lunch. Thank you.